All right, so sometimes we just have to take questions as they come and just see what eventuates. So the first thing says, find the derivative of sine inverse of x plus x square root 1 minus x squared. Okay, so what would the derivative equal to? dy dx is equal to derivative of sine inverse of x. What's that equal to? That's equal to 1 over the square root of 1 minus x squared, isn't it? Plus the derivative. So derivative of the first, so let's write this as x times 1 minus x squared to the power of a half. Yeah. Plus the derivative of the second expression. So it's the derivative of the first, which is 1. Might do it here. 1 times 1 minus x squared to the half, plus the derivative of the second expression, which is a half times 1 minus x squared, derivative, take from the power, times the derivative of the inside, which is negative 2x, times, just in a different colour, times x, which was the first function. So now if I sort of tidy that up to a little bit, I'm going to have 1 over the square root of 1 minus x squared, which is what we started with. What have we got? So I've got plus the square root of 1 minus x squared. And then this last term, negative 2 times a half, is negative 1. X times x is x squared, so it's minus x squared over the square root of 1 minus x squared. I sort of keep working these two terms together. I'm going to have, I need a common denominator. So if you like, I've got the square root of 1 minus x squared. And I'm going to times that by the square root of 1 minus x squared over the square root of 1 minus x squared. And then I've just got my minus x squared over the square root of 1 minus x squared. So in here, I'm going to end up with everything squared. So I just get 1 minus x squared. So that's going to equal, get rid of that. So I'm going to have, undo that, I'm going to have this 1 over 1 minus x squared plus 1 minus x squared all over 1 minus x squared. So what's that? That's equal to 2 minus 2x squared over. So that's equal to 2 outside of 1 minus x squared square root of 1 minus x squared. So that's the same term, 1 raised to the power of a half, which is 2 square root 1 minus x squared. Geez, that takes some work. I'm glad I left you all that room. Yeah, so you might need to work down the side a little bit there, boys. So the final answer we get in all of that, I believe, don't worry, I'll check it, is dy dx is equal to 2 square root 1 minus x squared. All right. Hence, evaluate the antiderivative. So this is going to be probably haven't covered yet in methods. It's going to be integration by recognition, isn't it? So what does it mean? I need to work out, so I need to work out that expression here, which is just about that expression there. All right. So I guess if this function here is y, not a new pen here, if that's y, that means that if I anti-differentiate both sides here, y is equal to 2 times the antiderivative of square root of 1 minus x squared dx, yeah? So bring that 2 across, so I'll say y on 2 is equal to the antiderivative, which is what I'm looking for. So the integral from 0 to a half of square root of 1 minus x squared dx is equal to, if you like, capital F of a half minus capital F of 0, where capital F of x is the antiderivative. Yeah? And the antiderivative is the y function, which is all of that. So that's simply going to be equal to sine inverse of x plus x square root of 1 minus x squared, all on 2 because it was a half of y, evaluated between 0 and a half, which is equal to, we'll take the half out the front, and I get sine inverse, I'll look at it, sine inverse of a half, which is pi on 6, plus a half times the square root of 1 minus a half squared, which is 1 minus a quarter, which is root 3 on 4. Subtract sine inverse of 0, which is 0. In fact, everything's 0. So let's evaluate that. I get a half of pi on 6 plus root 3. Root 4 is 2, so it's root 3 on 2 times a half, which is root 3 on 4. So I'm going to have pi on 12 plus root 3 on 8. Okay, bit of fun. Sorry about the lack of room, lads. At least this derivative looks a little bit easier to get, doesn't it? So if y is equal to x e to the 2x, dy dx is the derivative of the first times the second plus the derivative of the second times the first. So if I take e to the 2x out the front, I get 1 plus 2x e to the 2x. That's not bad. So if we can just simplify that further, well actually I probably won't simplify it, simplify it, dy dx is equal to, just expand it again, e to the 2x plus 2x e to the 2x. Because now I'm looking at that x e to the 2x here in part B. So there's part A, happy with that. All right, part B, I'm going to bring that expression down. Dy dx equals e to the 2x plus 2x e to the 2x. So now if I integrate everything with respect to x, I have equality. So therefore I get y minus the integral of e to the 2x dx is equal to 2 times the integral of x e to the 2x dx. So I might leave the 2 over there for now. So there's the term that I'm looking for. Well, here's the expression I should say I'm looking for. What is y? Well, y was just x e to the 2x. Subtract the antiderivative of e to the 2x, which is 1 on k, e to the 2x. That's equal to 2 times the integral of x e to the 2x dx. Can I tidy up left-hand side? I'm going to have to bring a half. What if I take a half out the front? E to the 2x. That leaves me with a 2x minus 1, 2x e to the 2x dx. So if I divide the 2 across, I'll have the integral of x e to the 2x dx is equal to 1/4 e to the 2x outside of 2x minus 1. Plus c. All right, so I think you're now in a position to have a bit of a go at the rest of at the end of the chapter. I guess we've covered all the different integration techniques, and there is a lot there. So just look, work through, practice them, get used to trying to identify the right process. Okay, so look, identifying the right process, I guess, is only half the battle, but it's an important one. There's so many areas in through here, that you can make algebraic errors. But getting the right process is a massive step towards the right answer. All right, well, let's have a look. I'm thinking the bottom expression is a quadratic factor in e to the 3x, a quadratic factor. It's a quadratic. So let's have a look. If I put u equal to e to the 3x, let's have a look. Du is equal to 3e to the 3x, sorry, du dx. So that means 1/3 du is equal to e to the 3x dx. Let's get ourselves a bit of space. And that means if I take the 4 out the front, I've got e to the 3x dx, which is equal to 1/3 du. So I'll bring the third out as well. 1 du. And u is equal to 3x, e to the 3x, so u squared is equal to e to the 6x. And so that becomes u squared minus 4u minus 5. Now that looks like something we can deal with. Equal to 4/3 outside of, was that u minus 5, u plus 1. So then 1 over u minus 5, u plus 1 is equal to a over u minus 5 plus b over u plus 1. 1 is equal to a, so we'll do some partial fractions work. If I put u equal to -1, I'll get 1 is equal to -1 minus 5 is -6. B is equal to minus 1/6. I put u equal to +5. I'll get 1 is equal to 6a. A is equal to 1/6. So we get our integral is given by 4/3 of a. Let's bring a 6 out the front as well. If I bring a 6 out the front, oops, 1/6 out the front, and that leaves me with a +1 over u minus 5 minus b, which is a -1 over u plus 1 du. So it's I'll just put it, it's equal to 4 on 18 outside of natural log of u minus 5 minus natural log of u plus 1, which is 2/9 natural log u minus 5, which is e to the 3x minus 5 over u plus 1, which is e to the 3x plus 1, plus some constant c. As I try to do, lads, I try to check my answers to see if I've got them right. And, you know, I get there most often. Makes it a real problem when you can't read the question accurately, doesn't it? Now, I'm going to do something I don't do very often. And I'm just going to leave it like that and say, well, if we change that negative sign, and I could, I feel quite certain, I wonder if I can. Oh, I can't quite rub it out. So that's the correct answer for that. If by chance you did it correctly, which I hope you did before I got to it, you would have got e to the 3x minus 1 over e to the 3x plus 5. Okay, so that is the correct answer for the question as it is written. And my answer is the correct answer for a different question. But I'm not, it's late and I'm not going to change it. off you go. Anyway, you know the process. That's what I was talking about a bit earlier, in fact. Technique is one thing, but attention to detail is such an important part of it. So let's see if we can bounce. If we can, I can bounce back on the last one. Here's one of those typical U substitution ones, isn't it? So I think we might have even moved. If we haven't done this one, we've done one very similar. U equal to 2x minus 3. Du dx is equal to 2. So 1/2 du is equal to dx. So there's my dx expression. So what's x minus 1 equal to? So if u is equal to 2x minus 3, that implies that x is equal to 3 plus u on 2. And so then x minus 1 is equal to 3 on 2 plus u on 2 minus 2 on 2. So x minus 1 is equal to 1 plus u on 2. All right, so let's bring it all together a little bit. So I've got the integral of the x minus 1 is equal to, we'll bring that half out the front. I get 1 plus u, so there's x minus 1. The square root of 2x minus 3 is u to the half, and dx is equal to another half du. Yeah. So what does that give me? That gives me 1/4 integral u to the half plus u to the 3 on 2 du, which is 1/4 outside of, add 1 to the power, divide by the power, which means we flip upside and multiply, plus add 1 to the power, flip it upside down and multiply, because we're really dividing by 5 on 2, plus a constant of some kind, which we can put in at the end, which gives me, actually, before we substitute in our u value back in, let's simplify this fraction term a little bit, yeah? So the 2 is obviously can come out the front, so I can put that as a half outside of. Now, u to the 3 on 2 plus u to the 5 on 2, oops, on 3 on 5, common denominator of 15, so over 15, cross multiply, so that becomes 5u to the 3 on 2 plus 3u to the 5 on 2, yeah? So let's take the 15 out the front, so we'll end up with 1 on 30 outside of. Now, when we have expressions raised to fractional powers, often we can take out that lowest fraction as a common denominator or a common factor, and then often be left with a whole number integer power that we might be able to group, expand, do something with. So in this case, I'm talking about if I take u to the 3 on 2 out the front, I get a 5 plus 3u to the 2 on 2, don't I? I don't need the over, that's all over 1. So from there, I get 1 on 30. U to the 3 on 2 is equal to u, 2x minus 3. 3 on 2 times 5 plus, well, 2 to the 2 is 1. 3 times 2x minus 3. So let's simplify that m bracket. 2x minus 3 to the 3 on 2, I get 5 plus 6x minus 9, which gives me 1 on 30, 2x minus 3 to the 3 on 2, 6x, what's that, minus 2? So if I bring a 2 out the front of that bracket, I'll get 2 on 30, which is 1/15. 2x minus 3 to the 3 on 2 outside of 3x minus 1. All right, that's a 4 there. 4, 3x minus 2. Looks better. All right. So, yeah. So, look, I think just the little power, that one, when we work with square root functions, often we end up with that u to the half, u to the 3 on 2, maybe a 1 on root x plus root x. So when we've got that factor of a half kind of thing in play, often we can take it out and turn something into a whole integer number. All right, now we're at the end of the exercise. Off you go.